Graph Theory Class 12 Video 2. In this video we're going to talk about Hamiltonian graphs, and in particular we're going to talk about a theorem which helps to determine if a graph is not Hamiltonian. But before we can actually get on to the theorem, we need to do a quick definition first for something which will be useful in the theorem. So a cut vertex is a vertex such that its deletion causes the number of connected components to increase. Okay? So this is quite an abstract definition, but the idea is a cut vertex is a vertex in a graph such that if you were to delete that vertex, you would break the graph up into two disjoint parts. You'd increase the number of connected components of the graph if you were to delete this particular vertex. And not every graph has a cut vertex, and some graphs have more than one cut vertex. So let's look at an example quickly. Okay, find all the cut vertices. So you just need to think what would happen if you delete a vertex. So this is two different problems, right? Let's do the first one first. So if you deleted this vertex right here, what would happen? Well, the new graph would look something like this, and this is still one connected component. So by deleting the pink vertex, you did not increase the number of connected components. So that means that that pink vertex is not a cut vertex. And similarly, this one here is not a cut vertex. But what happens when we delete this one? Well, when we delete this one, we get something that looks like this. And now we've got two connected components. Okay? We've got two connected components and we started with one. So by deleting this vertex, we increase the number of connected components, which means that that vertex is a cut vertex. So I'll just do it in red. Okay? That's a cut vertex. And similarly, if you think about it, so is this one and so is this one. So they're the cut vertices. Okay, the red ones are the cut vertices for this particular graph. So let's move on to the second graph. Okay. Well, again, you can imagine, just testing a random vertex. If you delete that vertex, what will happen? Well, the graph will look like this, which is still connected. It's still one connected component, so that's not a cut vertex. But if you delete, say, this one, if you delete that one, then what's going to happen is you get a graph that looks like this. So now it's two pieces, which means that this pink vertex is a cut vertex. So I'll color it in red. And similarly, this one here is also a cut vertex. And they're the only cut vertices for this graph. And like I said, not every graph has a cut vertex. For example, a really easy example is if I draw this graph here, C3, the triangle, this one here has no cut vertices. And that's perfectly fine. That doesn't matter at all. Okay? So that's cut vertices. Let's move on to the theorem. It's a theorem in three parts, okay? And it's an important theorem. So it just says if a graph has a cut vertex, then it is not Hamiltonian. Okay? If a graph has a cut vertex, then it's not Hamiltonian. The second condition, the second part of the theorem, says if a graph has a leaf, then it's not Hamiltonian. So a leaf is if you remember, a degree 1 vertex. So a vertex with degree 1. And the final part of the theorem says if a graph is bipartite with different partition sizes, so that's important, okay, then it's not Hamiltonian. This is a really important theorem and it's a lot to digest, so I recommend that you really take a minute to sort of take in this theorem, okay? It's very important. Some important notes is this theorem, it's not complete. It does not completely classify Hamiltonian graphs. Okay, so the theorem does not completely classify Hamiltonian graphs. And what I mean by that is this theorem, it's a bunch of one-way implications. So it's saying stuff like, if you have a cut vertex, then you're not Hamiltonian. But the converse is not necessarily true. Like, just because you don't have a cut vertex, that does not mean that you are necessarily Hamiltonian. It's possible to not have any cut vertices and still not be Hamiltonian. Okay, so let's do some examples, because to get your head around this theorem, you really need to do examples. Okay, so the question is just, are these graphs Hamiltonian? Are these graphs Hamiltonian? Okay, so I look at this first graph right here, and you know, you could try and just do some sort of trial and error to try and find a Hamiltonian circuit, but it will be difficult. So what you should really be doing is trying to apply the above theorem. So you look at this and you say, does it have a cut vertex? Well, once you have a bit of practice working with cut vertices, you notice that no, there's no cut vertex here. Does it have a leaf? No, all the vertices have degree higher than 1. So is it maybe bipartite? So I'm just going to try and colour in the vertices, because remember there's a theorem which says bipartite just means two colourable. Okay, and yeah, it's bipartite. Like, I can colour it in with two colours, red and blue. Okay, so it's bipartite, but that by itself does not mean that it's not Hamiltonian, because the theorem says bipartite with different partition sizes. Okay, bipartite with different partition sizes. So what I mean by that is, how many blue vertices do I have and how many red vertices? I have 4 blue vertices and 5 red vertices. Okay, so this means by the above theorem that it is not Hamiltonian. It is not Hamiltonian. Okay, by the above theorem. So let's move on to the next example. So again, very similar to the one above. Okay, it's no cut vertices, no leaves. We know that it's bipartite, and I can color it in for you right now. Okay, like this. And now the question is, how many blue and how many red? Well, if you count, there's 1, 2, 3, 4, 5, 6 blue and 1, 2, 3, 4, 5, 6 red. So this is like the worst case to be in, because we can't apply the above theorem. This theorem only works when the partition sizes are different. But right now, they're both size 6. So we just can't apply the above theorem, which means that all we can do is try and, you know, do some trial and error, trying to find a Hamiltonian circuit. So it's just going to be try your best. So I'm going to try and draw something like that, and that happens to work. Okay, so that thing I drew is a Hamiltonian circuit. So is it Hamiltonian? Yeah. Okay, but notice I didn't know it's Hamiltonian because of any sort of theorem. I just happened to find a Hamiltonian circuit. Okay, let's move on to the next one, this flower looking thing. Well, this example is going to be nice and quick because I see a cut vertex right here. Okay, that's a cut vertex, so it is not Hamiltonian. Okay, easy. Just use the above theorem. And let's move on to this last example right here. This one here is also relatively easy because I see a leaf right there. So it is not Hamiltonian. Okay. I want to emphasize that this theorem, it is not a complete classification of Hamiltonian graphs. Okay, so if we look at this next example right here, okay, in this example here, you notice that there is no cut vertex, no leaves, and it is not bipartite. Okay, like you can test these things yourself and see, like it is not bipartite. You could color like green, well, green's a bad color, like red, blank, red, blank, red, blank, but then this middle one, what color do you color it? You're in trouble. So it's not bipartite, okay? But it is still not Hamiltonian. Okay, and it's relatively easy to see. I mean, no matter where you start, like, you can't visit every vertex exactly once and return to where you start. Okay, it's impossible to visit every vertex exactly once and return to where you start. So even though it doesn't satisfy any of the conditions of the theorem, it's still not Hamiltonian. This theorem, it's not a complete theorem, it's just a helping, it's like a partial result. It helps you partially classify Hamiltonian graphs. Okay? And in general, you hope that you don't run into examples like this, because examples like this are just more difficult. Okay, that's the end of this example, and that's the end of this video.